start. Today we start with Maxwell equations. Okay, let me write. Okay, Maxwell's equations. Well, so far we have seen electrostatic equations, magnetostatic equations, equations for electric field, equations for magnetic field, the equations used, for example, in Faraday's law. And now the question is, are the Maxwell equations different from the other field equations? Do they add anything to the previously described phenomena, or is there any other electromagnetic phenomenon that was not discussed in previous chapters? Or do Maxwell's equation define these yet unknown properties of electromagnetic field? Well, in general, the answer is yes. In fact, well, we don't need to go far to find applications which could not be treated using, for example, Faraday's law. Uh, uh, take for example induction of voltage in a loop. Well, the Faraday's law gives us a very accurate statement of how voltage is induced and the maximum values of voltage, about the maximum values of voltages. But the question is, the problem is the two loops, first loop and second loop. In all the problems, in all our problems, two loops were located in a short distance from each other. That's why we didn't take into account the time lag which is needed to travel the energy from the first loop to another loop. If we put two loops, okay, this is first loop and this is, for example, second loop, very far from each other, it is obvious that, okay, very far, it is obvious that energy from the first loop reaches the second loop in some time. Okay. And the question is there any lag in time between switching on the current in the first loop and detection of the induced voltage in the second loop, because of the distance between two loops? Well, Faraday's law says nothing about this time lag. And well, uh, intuitively we know that there should be some time lag in transferring energy from the first loop to another loop if the distance between them is very long. For example, the uh, for example, the signal uh, radio signal from the space probe called Pioneer. Well, probably you know about this space probe Pioneer 10, which is far far as 12.2 billions uh, of kilometers far from Earth, and the time which is needed to receive signal from this space probe was something about 11 hours 11 hours and 18 minutes. Well, you can see of course, the signal, or in signal in this case, is energy. Energy cannot reach from one point to another point in one instant. It requires some time, and if we want to find the velocity, we find something about the speed of light. And well, it seems obvious that if we want to transfer energy to very far distances, there will be time lag or in order to reach energy from one point to another point. However, the Ampere's law and Faraday law says nothing about time lag, and Maxwell's equations are in fact four postulates which we introduced in the previous chapter, with a modification to Ampere's law to account for finite speed of propagation of power, or finite speed of propagation of energy. Well, okay. For uh, huh? Let me copy the four postulates, or mm, four implications which come which which come from Maxwell's equations. Well, very first and very obvious conclusion is interdependence of the electric and magnetic fields. Okay, electric fields and magnetic fields are related to each other. Well, it is obvious. And a second conclusion says the existence of electromagnetic waves. So far, when we discussed Ampere law and Faraday's law, we didn't take into account the electromagnetic waves. But Maxwell's equations and Maxwell's observations conclude that conclude that the electromagnetic waves exist, and finite speed of propagation of electromagnetic waves, and the another observation is the electromagnetic waves travel through the space with finite speed, and fourth, and the final is the propagation in free space is at the speed of light, and the light itself is an electromagnetic wave. Okay, well, let's take a look at Maxwell's equations. Okay, these are the four field equations before and after Maxwell's modification. If you pay attention, only one equation was changed. This is the Ampere's law, and Maxwell added this term into the Ampere's law. Uh, Let me draw it in, maybe in green. Okay. Comparison between the two sets revealed that the only difference is in the last term of 11.6. Last term is this we have discussed. This term is a current density. This term is current density and is called the displacement current density. Or the over the T displacement current density. And and J, we know, is just the current density in the conductor. We already know about J. Well, let's try to uh, let's try to show that equations equations uh, field equations before Maxwell's modification uh, are not consistent with the continuity equation. Uh, in order to do so, let's take the equation 11.2, this equation, and let's try to manipulate with this equation. And so we have the rotor of magnetic field intensity equal to the J. This is the one of the field equations before Maxwell's modification. And if we take the divergence of the both sides of equation. So according to the properties of vector fields, this term should be 0. Why? Because according to the properties of vector fields, divergence of rotor of vector field is 0, and this implies that divergence of J also 0. Okay. On the other hand, if we take uh, equation 11.6, if we take this equation and try to manipulate with this equation, 11.6 was equals to J plus displacement current density, and if we take the divergence of both sides, what we get, H equals to divergence of J plus divergence of displacement current density. And what we get is so we know that this term is 0. We know this, and what we get is the divergence of J will be equal to minus the T divergence of D. And from our previous knowledge, we know that this is equal to rho V. And we get that divergence of G equals to minus D rho V over the T. So this equation is exactly the continuity equation. We have already seen this equation also in our previous lessons. So it means that introduction of displacement current density. So if we look here, introduction of displacement current density, this term makes equation 11.2 this equation. Here we introduce current displacement current density. If we introduce displacement current density, makes equation 11.2 consistent with the law of conservation of charge, or makes this equation consistent with the continuity equation. So let's see one example. Okay. Displacement current in a capacitor. So we are given a capacitor connected to the voltage source of alternating current. VC voltage source produces the voltage of Vs sine omega t, and okay, sine omega t, and we need to calculate displacement current in the capacitor. Okay. Displacement current means the okay current inside the capacitor. Well, from it is obvious that it is obvious from our circuit that displacement current ID should be equal to the current of IC. That's why we can easily find IC by okay, first method. Sorry, let me write in blue. So we can easily find IC by the equation C dVc over dt, where Vc is Vs sine omega t, C d the t Vs sine omega t, and this will be equal to C Vs omega cosine omega t. Okay, this is obvious. However, we can solve this in another way also with the help of with the use of displacement current density and electric flux density in the capacitor. Well, let me open a new page. Okay, so the another way to solve, well, this solution simply comes from circuit theory. Simply we from this picture we can see that ID displacement current is equal to the IC, and IC comes simply from circuits theory. And now uh, from the point of view of electromagnetics, so for a parallel plate capacitor, electric field intensity E was equal to Vc over D where Vc is Vs sine omega t over the unit of measurement is volt per meter. Okay, it doesn't. And the displacement current density JD we said is equal to d over dt, and d is in turn is equal to epsilon multiplied by electric field E, and we get that displacement current density equal to epsilon the E over the T, which is, instead of E we put this epsilon, so the T Vs sorry Vs sine omega t over d, and if we derive with respect to time, we get epsilon over d Vs omega cosine omega t. Now we know JD. Now we can compute ID, which is integral of JD over the surface S, and is equal to epsilon over d Vs omega cosine omega t multiplied by integral of S ds. And so and ID becomes equal to epsilon over d Vs omega cosine omega t multiplied. The value of this integral is simply S multiplied by S. Okay, and for parallel plate capacitor, this term gives us the capacitance of our capacitor. Yep. Epsilon multiplied by S over D gives us the epsilon S over D gives us the capacitance of our capacitor. Now ID becomes Vs multiplied, oh sorry, let me write C multiplied by Vs multiplied by omega cosine omega t. And if we look to our previous answer, the answer is exactly the same. And the displacement current is equal to displacement current in the capacitor is equal to C multiplied by Vs by omega cosine omega t. Here we have an example in which the displacement current is actually necessary to account for the behavior of the circuit. Well, in its absence, in the absence of displacement current, we must assume that current cannot flow through the capacitor. In circuit theory, displacement currents are not normally used or assumed. Well, in circuit theory, you assume that current doesn't flow through the capacitor. And to account for, for their effects, the common explanation is that the plates of the capacitor are alternately charged with positive and negative charges. And well, in fact, the displacement currents occur through the capacitor. Well, now we have another problem. Okay. The next problem is a slab of perfect dielectric material, the relative permeability relative permeability of 2 is placed in a microwave oven. The oven produces an electric field as well as a magnetic field. Assume that the electric field intensity is uniform in the slab and sinusoidal in form and that is perpendicular to the surface of the slab. The microwave oven operates at a frequency of 2.45 GHz and produces an electric field intensity with amplitude of 500 volt per meter inside the dielectric. Calculate the displacement current density in the dielectric. And the next question is there a displacement current in air? If so, calculate it. Okay. We are given a slab of dielectric which is placed inside the microwave oven. Okay. And we assume that electric field intensity is uniform and directed perpendicular to the surface of our slab. And the electric field intensity E is equal to the E0 multiplied by sine omega t, where E0 is 500 sine omega t, where omega is 2pf, and which is equal to 4.9 p 10 to the 9 radians per second. Okay. First question is A. Calculate the displacement current density inside the dielectric. Well, uh, from the previous slides, okay, from the previous definitions, okay, maybe from here also, we know that this is JD and JD is equal to change of electric flux density by time. And okay, we know this. Now we need to compute D, electric flux density in dielectrics, and after that we can compute the JD. Okay, D equals, from the definition, D equals to epsilon multiplied by electric field intensity, where epsilon is equal to epsilon 0 by epsilon r, and electric field intensity E equal to E0 sine omega t. Okay. Okay. Now we know D, and now we can compute the numeric values for D. Okay, where epsilon 0 is equal to or better, let's compute derivative of D with respect to time, and after that we'll put the numeric values. So the D over the T will be equal to epsilon 0 epsilon r E0 omega cosine omega t, and well, we are interested in JD. JD will be equal to epsilon 0 is 8.854 10 to the minus 12 multiplied epsilon r is 2, E0 is 500, Okay, omega is 4.9 p 10 to the 9 multiplied by cosine omega t. So cosine omega t and is equal to, so 8.854 multiplied by 2 multiplied by 500 multiplied by 4.9 multiplied by p equals and divided by 1000. Okay, JD equals to 136.3 cosine omega t ampere per meter squared. Well, this is the displacement current density inside the dielectric slab, which is placed in the microwave oven. So, well, you can see that it is not so big, not so big number. However, this current density is responsible for heating your objects which are placed inside the microwave oven. So let's have a rest for 10 minutes. After that, we start our second part of our lesson.